Please telling us about the propagation of chaos and meeting limits.
Okay, so thank you very much. Thank you. I'd like to start by thanking the organizers for first inviting me and for organizing this day. So my name is Pierre Le Bris. I'm a postdoc at IHES under the supervision of Thierry Baudineau. And before that, I was a PhD student nearby in Jussieu under the joint supervision of Arnaud Guillain, who's in Clermont-Ferrand, and Pierre Montmarché, who's in the lab, the LGLL. And what I would like to talk to you about today is some joint works I've done during my thesis with both of them. And I'll also mention some work with Laetitia Colombani, who's a postdoc in Polytechnique, and Christophe Poquet, who's maître de conférence in Lyon. Okay, and the theme of my thesis, or the overall theme of what I would like to talk to you about today, is propagation of chaos. So where does it come from? What's the idea? So the starting point, the historical starting point for what I would like to talk about, comes from the kinetic theory of gases. Okay, if you take a gas in a room, you know that you have many points of view that you can take to study this gas. You know that you can take a macroscopic point of view. You can consider observables such as the temperature of the gas, the pressure of the gas, and so on and so on. But you also know that a gas is a large collection of particles that interact with each other. So you can take a microscopic point of view, where for each individual particle, you write Newton's law. Okay, and you have your particle, for instance, in Boltzmann case, which will collide with each other and so on. But the thing is, if you take that microscopic point of view, it's quite unfeasible in practice because there are so many particles to consider that you can't actually follow the thing. Hence, an in-between point of view that was suggested, which is a mesoscopic point of view, and which consists in looking at the statistical description of the system. Instead of looking at each individual particle, you look at the distribution of one typical particle in this system, a statistical description. But in doing so, like Boltzmann in the 19th century, building upon Maxwell's work, showed his famous H theorem, which consists in saying that the entropy, the physical entropy of the system, can only increase with time. Now, this sparked a bit of criticism, among which the fact that if you have an entropy that can only increase, it means that you are non-reversible in time. But if you write Newton's law, you know that your processes should be reversible. So there were many answers to this seemingly intricate paradox. And the one I would like to focus on is one of the answers given by Katz, and which was then generalized by McKean, which is propagation of chaos, and which consists in looking at one of the assumptions that Boltzmann made, which is the assumption of molecular chaos. Indeed, if I look at my statistical description of the system, I know the distribution of one particle, but I'm missing one piece of information. And the information I'm missing is what's the joint law of two particles. If I take two particles in this gas, what's their joint law? And the assumption that Boltzmann made was to say, if I take two particles in this gas, they're independent, which intuitively sort of makes sense, which is, say, if you consider a cloud of particles, there are two given particles have so many neighbors to consider that in the end, they sort of forget about each other specifically, and they only see each other through the overall, their common law. And Katz's approach was to say, yeah, okay, obviously, when you look at the microscopic point of view, those two particles are not independent. If they interact with each other, they become correlated. But if I let n, the number of particles, go to infinity, they become more and more statistically independent. And that's the sort of phenomenon I would like to show on specific cases. So the sort of toy model for on which I'm going to work is an SDE. I describe my particle system as a stochastic differential equation where each particle is represented through a quantity x. X most likely its position, but you can be a bit more creative. Each particle is driven by a Brownian motion. I assume all my Brownian motions to be independent, and my particles interact with each other in a mean field setting, meaning that they all see each other according to a kernel K, which so far, I mean, at this stage, K is just a function. Okay, it's just a toy model on which I'm going to talk a bit. Okay, and I'm going to make the assumption that my particles are exchangeable, meaning that I can relabel them. It won't change the overall law of the system. So the question is, okay, what happens when the number of particles goes to infinity? And the phenomenon, the propagation of chaos phenomenon, in a system of n interacting particles, as n increases, two particles become more and more statistically independent. Okay, so far I'm waving my hands, but I will be more precise concerning this phenomenon later on. Okay, so I'm interested in the limit as n goes to infinity. So the first thing I'm going to do is, okay, try and find a good candidate for my limits. If I do things, very naively, first notice I look at the empirical distribution of the system. Okay, and I realize that this 1 over n sum of k is k convoluted with this empirical distribution. Now, if I expect first all my particles to have the same law because they are exchangeable, and the second, if I expect my particles to become independent, well, I sort of guess that this empirical distribution will converge via some sort of law of large numbers or something like this to the typical law of one particle of the limit. Hence, sort of my candidate for the limit, which is this Matkin-Vlasov SDE, where I still have my Brownian motion, and the interaction is rewritten as an interaction with its own law, where here rho bar t is the law of x bar t. Okay, and so this thing up there is what I'm going to call the particle system, and down there is the nonlinear limits. It's the x bar t is a random variable. It has a law, and it interacts with its own law. It's like saying that in your cloud of particles, you only see the other particle according to the common law of everyone. Okay, so it's a nonlinear equation. Okay, and so basically what I want to show is that the top converges to the bottom in some sense. To these two probabilistic objects, I can link a more PDE object, which consists in looking at the law, the joint law of my particle system. If I write Fokker-Planck's equation, i.e. the equation that describes the time evolution of my law, I get the time evolution from my law. And likewise, if I look at the nonlinear equation, I can look at its nonlinear, PDE, dt rho bar t plus gradient, divergence, k convoluted with rho bar t equals sigma Laplacian of rho bar t. Okay, so when I was talking about the microscopic point of view, it was, sorry, what have I done? It was the, it was the particle system up there. And when I was talking about the mesoscopic point of view, it was this equation here, which translates the time evolution of my statistical description of my system. Okay, so I have two objects, the red ones, which are probabilistic objects, the blue ones, which are more like PDE objects. And I want to show that the top converges towards the bottom. More precisely, you see that this is an n-dimensional thing. This is a one-dimensional thing or d-dimensional thing. What you actually want to show is more concerns the marginals. Okay, so you look at the marginal of your system. So you take the first k variables, you integrate over the rest. That gives you the joint law of my first k particles. And because of the exchangeability assumption, that gives me the law of any subset of k particles within my n particle system. And the sort of result I want to show is chaos at time 0 propagates over time. Meaning that if I take the limit as n goes to infinity of my marginal, it converges towards the tensorized law. The tensorization is the independence, i.e. the chaos. And I want to show that it propagates. I'm going to assume it's true at t equals 0. I want to show that it holds at later time t. So this is propagation of chaos. Once again, I'm waving my hands. I'm not telling you in what metric, in what distance it converges. Okay, and actually choosing the metric, choosing the distance is the sport itself. And because I have an exchangeable particle system, the other phenomenon which is equivalent, is the mean field limit, which consists in looking at the empirical measure and showing that it converges to rho bar T. Okay, these two formulations, provided my particle system is exchangeable, are equivalent. Not really in a quantitative way, but qualitatively they are equivalent. Yeah.
Question, but chaos, what is chaos?
Chaos actually is a fancy way of saying independence. Okay, chaos is actually my independence. It's from a joint law. I have tensorized law. Okay, that notation is okay?
So you're saying that if they are zero, they keep independent?
Yeah, or if they are close to being independent, if actually this distance between those two things. Yeah, that's exactly the point. Okay, so this is the sort of thing I want to show. And I want to try and show this in some specific cases, keeping in mind two like sub-goals. The first sub-goal I'm going to have is uniformity in time. Why? Because you see that a priori this limit is pointwise in t. For each t, I have a limit in n. The question is, can I make that limit in n uniform in t? This has a sort of, this is not just a mathematical question for the fun of it. There is application. You know, if you want to, you always see one as an approximation of the other. If you want to get information, I don't know, on the long time behavior of one, can you use the other, and so on and so on. And what I hope to convince you at some point is that this has a link with the long time behavior of the processes. The first link being that, as you'll be able to see, most of the methods that we have, some of the methods that we have to show propagation of chaos actually come from adapting methods to show long-time convergence of particle system or processes. The one way to see it quite easily at this stage is that you take sigma equals 0. Okay, so you imagine you have no Brownian motion, you're only left with a standard ODE. And you test your empirical measure against some function f, which is sufficiently smooth. If you look at the time evolution of this, okay, you can rewrite this and you realize that mu t and your empirical measure is also a solution of this equation here, of this nonlinear equation, at least in a weak sense. Okay, sigma equals 0, so I don't have this. If sigma is different from 0, you have like random terms that keep appearing, so it gets a bit more complicated. But I mean, sigma equals 0, you have mu tn and its limit, which are both solution to the same equation. So actually proving propagation of chaos boils down to a question of the stability for the PG. Stability in the sense that if I take two initial conditions that are different, can I control it? Can I control the evolution of this difference? So this, okay, uniformity in time would be one of my goals. The other goal that I keep at the back of my mind is that I want to be able to deal with singular interaction. And the type of singular interaction that, the type of, framework or convention I'm going to use is the one of Riesz interaction, in which k is the derivative of a potential j, and j is singular in 0. Okay, meaning that this is not well defined at 0. And in this sort of framework, there are a few cases of interest. Okay, if you take S equal d minus 2, you're in the case of Coulomb interaction. And so the first order system is an approximation of Newtonian dynamics. If you take in dimension 2, S equals 0, so you take a logarithmic and you take the derivative of the logarithmic and you sort of rotate it. You've got something which is known as the 2D vortex model, which I'm going to speak about later on, which has application in fluid dynamics. If you take d equals 1 and log gas, you've got Dyson-Brownian motions, which has application in random matrices and therefore in telecommunication, I believe. But you have also applications to biology, to, okay. Okay, so those are the two goals, uniformity in time and singular interaction. So I want to show that either mu tn converges to rho bar t, or that rho bar, the k marginal converges to rho bar tensorized k time. So I want to use this sort of talk as an opportunity for me to like compare at my small scale, like some methods that are used, one more PD and one more probabilistic. So I won't be able to do like a fully fledged review, first of all, because I don't have the time, and second of all, because I don't have the knowledge, but I still want to have 2 slides on which I can tell you, okay, this is the sort of thing you can do, this is the sort of things you can do. So I regroup the methods into like fixed categories, but obviously these categories are quite porous. Maybe some work belongs to many, okay? And I choose I leave many works behind, and the names I choose are biased. So the first historical method, at least the one that was used by Mackin and then popularized by Snitman in the 90s, is a coupling method. Okay, comes from the fact that you want to show convergence of one probability distribution towards another, and the good object and the good distance is the Wasserstein distance, which has regained in popularity recently thanks to theory of optimal transport, and which consists in saying, okay, if I want the Wasserstein distance between measure mu and measure nu, I take x distributed according to mu, y according to nu, and I take the expectation of the distance. Now, if I do so, I have many ways of choosing the vector x, y. I can, for instance, take them independent, or I can be a bit more clever. And taking the infimum over all possible coupling yields a distance. And so the coupling method consists in saying, okay, instead of taking the infimum over all coupling, I'm just going to consider and construct a specific one, which is therefore bound by distance. It will be a quantitative. I will speak a bit about this method. The second type of method would be more, yeah, sorry.
So you said that you wanted to prove propagation of clusters, but there you are. So you want to prove just that you have a limit.
So propagate. I want to show that either the empirical distribution converges towards rho bar, which is the mean field limit, and equivalently, it's equivalent to the propagation of chaos, which is the marginal converge to a tensorized law. Okay.
So that's equivalent. So
those two things are equivalent, yeah, in the case of exchangeable system.
Maybe another question.
Yeah.
For the coupling method, is there some result about the rate?
Yeah, I'm going to come to it. It will be the first type of work I'll mention. So I'll speak about these two methods here, and the other ones I'm going to leave out. But I'll be more specific concerning this method. No. Yeah, if you have any questions, please interrupt me and tell me if I'm speaking too fast. I know it's something I tend to do. But okay, so the more PD method consists in considering a good quantity, an energy or an entropy, derivating it in time, and prove it's decreasing. Okay, this is also something I'm going to do. Recently, BBGKY hierarchies have regained again in popularity. It consists in considering the joint law of K particles. So you take the equation, the Fokker-Planck equation associated to the law, you integrate it over the n minus k last variable, and you realize that the law of K particle depend on the law of K plus 1 particle. So we've got like an iterative procedure, and along this hierarchy of equation, and along that hierarchy, you can, I don't know, prove entropy estimates as the Lacker did, or propagate LP bounds, which will then allow you to extract a convergent subsequence and so on. I will maybe mention BBGKY hierarchies very fast because there is an interesting result recently proven by Lacker. Obviously, because you're looking at convergence of measure, you can show that it's a tight sequence or it's a compact sequence, and you prove tightness of the sequence of measure and then uniqueness of the limit, which will give you a non-quantitative but qualitative convergence. Also, you can use, like recently also, weak norms and Lyon's derivative calculus, meaning that you're interested in errors that you make, such as this one. If you take your empirical measure and you hit it against a test function, how far are you from the nonlinear thing? So this amounts to looking at the semigroup and looking at the time evolution of your semigroup. And so there's a master equation, and okay, there are many things currently being done. So as I said, I'm going very fast on all this. A few sort of classical course by Snitman or Méliard. Recently, some review by Pierre-Emmanuel Jabin and Zhenfu Wang on singular stochastic particle system, and one very recent review by Chantron and Diez, which I quite enjoy, which is in 2 parts, and I can only recommend it if you're interested. Okay, so I'm going to focus on 2 problems, one of which will consist in looking at the coupling method, a probabilistic object, and the other one will be consist in more PDE approach to the same problem. Okay, so the coupling method, my goal is to couple like rho Tn and rho bar tensorized n time. So this amounts to simultaneously constructing first a solution of my particle system and n independent copies of my nonlinear limits. Okay, and I want to show that I want to construct those two things simultaneously such that they will converge to one another. And the first method, at least the method popularized by Snitman, is the synchronous coupling, which consists in saying, okay, I need a Brownian motion in both cases. I'm just going to use the same one. If I do so, and I look at the difference of my two solutions, I realize that the Brownian motion cancels out, and I'm only left with a deterministic drift. And this deterministic drift, I can actually bound it, consists in the difference of my two drifts, the difference between this and that.
What is A or AS?
AS is just a process that I will define. It's the one thing that appears here. It's okay. I use Ito's formula on this thing here. There's an AT dt that appears, so a quantity that I just call AT, and I just bound this AT by the absolute value of the difference. It's because I do this because actually there's a sign that appears, quite a complicated expression, but just in the end it's bounded by this thing here.
So you're just integrating the equations of motion.
Yeah, exactly. Just integrating. There is even no Ito because the Brownian motion has disappeared. Okay, so I'm left with this difference of the drift here. And as I said, the one thing I want to use is some form of low Flash number. So I'm going to introduce this 1/n sum of k with the independent nonlinear processes. And now I'm left with two objects. On the first one, I use the sort of regularity of k. I'm going to, for instance, assume that k is Lipschitz continuous. And on the second one, I use a low Flash number. I have independent copies of x, all share the same low rho bar. I jump a bit in the calculation, meaning that the expectation of the difference can be written in this way or can be bounded in this way. By Grunwald lemma, you are able to conclude on this control here. Grunwald lemma is actually the one thing that's gonna, usual thing that's gonna have you the distance at time t controlled by the distance at time 0. This thing here now controls my Wasserstein distance. And on the other hand, this thing here, I can just choose whatever initial conditions I want. I can, in particular, choose the initial configuration distributed according to my optimal coupling. And thus, I get like one typical result of propagation of chaos. This is the typical result. It basically tells you that, okay, if at time 0, this thing here converges as n goes to infinity, this thing here converges as n goes to infinity at later time t. It's also, you see that the error comes from two things: the propagation of an initial error that you might make on your configuration, plus 1/√n or something that comes from your large number, the fact that you don't have exactly the same drift here and here. And it's also an example of non-uniform in time propagation of chaos because of this exponential term here that comes from the Grunwald. Okay, if you want this quantity to be smaller than a given epsilon, the choice of n will actually depend on the time t itself. Okay?
And instead is the parameter that is defined from where?
N?
L.
L, where L is, sorry, it's the Lipschitz constant of k.
Okay.
It's the Lipschitz constant of my interaction. I assume my interactions to be Lipschitz. Good question, thanks. Okay. So one way of making this uniform in time would be, for instance, to add a contracting deterministic drift. So now in my system, I add a gradient of a convex function in both cases. So I use a confining potential on my particle system, which I expect to find again in my nonlinear limits. And if I write down again the evolution of the distance, I have now this term here that appears, okay? And from this term here, if U is lambda strongly convex, I have a lambda term that will help me control the previous term that I had. Okay, so this is an example now of a uniform in time propagation of chaos. Okay, if I take lambda big enough, greater than 2 times my Lipschitz constant, this thing here, will disappear with time, and I'm only left with this equation here. Okay.
And if you don't have a deterministic drift, are there ways using coupling to obtain the uniform in time?
So to my knowledge, I'm not entirely sure. Okay, all works I've seen using coupling methods use the drifts in somehow. So now confining potential. Now the one thing I'm going to talk about is a non-convex confining potential. So you can sort of work your way around if it's not super deterministically okay. Using no confining potential, not to my knowledge, using purely a coupling method. Using other method, yes. Using purely a coupling method, I'm not sure. Okay, so here, for instance, I'm going to assume that I'm going to try and work with a non-convex potential U to see what happens. And obviously, you see that I can't use a synchronous coupling. So what I have to do is actually use the noise a bit more smartly. Okay, so this is the first work I want to talk to you about. It concerns the kinetic case. Now I look at a second order system. So now each particle is represented through 2 quantities, position and velocity. The derivative of the position is the velocity, and the derivative of the velocity is the sum of the force. I assume once again that I have a Brownian motion. I have a friction term, a confining potential on U, and once again an interaction, which here I'll just write as the gradient of some W. Once again, I can sort of guess the limit. Everything should appear quite nicely, and then once again, this should become a gradient of W convoluted with its own law. And the assumptions I'm going to make is that my confining potential and my interaction both yield Lipschitz continuous forces. One of them I give Lipschitz constants Lu, and the other one Lw. And I'm going to assume that U is confining, but not necessarily convex. Okay, think of a double well potential. Typically, that's the one thing I want to deal with. Okay, so I want to simultaneously construct 2 solutions of those 2 processes. Okay, so here I just put BI1 and BI2 as sort of stand-ins where I try to figure out what I can do. Now, as I said, I need to play with the Brownian motion, and if I take the synchronous coupling, once again the Brownian noise disappears in the infinitesimal evolution. That's what we've just seen, which means that the contraction of a distance can only be induced by the deterministic drift. That's the example we've just seen. So in the case of a double well potential, it's not true. But here you can sort of identify a region of space. You just need to do some calculation that in this region of space, you have naturally contraction. Okay, if it's just some calculation, if the difference of the position and plus the difference of the velocity is close to 0, I have a natural deterministic contraction. This just appears in the calculation. So I know that in the vicinity of such space, I can use a synchronous coupling. Otherwise, well, I need to use the noise to get the processes closer together. What I'll do is I'll consider what is known as a reflection coupling or mirror coupling, which consists in reflecting one of the Brownian motions in certain directions so that one can be seen as the mirror of the other. You can explicitly write this. Why would you do this? It's because now if you look at the difference of the 2 processes, it maximizes the variance of the noise in the direction on which you need the processes to get closer together. You maximize the noise in this direction. But now you're going to tell me, yeah, but if you maximize the noise, what tells me that it's going to get closer rather than further apart? So what you need to do, what you can do, is you modify their distance by some concave function. If you modify it by a concave function, it means that contraction has more effect than an expansion of the same value. Okay, if you look at the concave function of your distance. Now another problem occurs. If you take a concave modification of your distance, it can no longer be equivalent to usual distance. Which means that you can only do this in a compact set. And that's where sort of the third behavior appears. I end up with three behavior. I know that when one particle goes to infinity, i.e. the position or the velocity gets super big, the confining potential and the friction term will bring my processes back to a compact set. And now I have identified three behavior on my system. When my particles are far away, they come back to a compact set. When they are in this compact, when they are near some space, this space here, the L1 distance will naturally contract. So you can use a synchronous coupling. And when it's not, it's in this compact set, but not on this specific subspace, you use the mirror coupling and the reflection coupling to get them closer together. Okay, so this was just sort of an example of how I'm going to construct explicitly a type of coupling, which I can now write this way, RC and SC being two functions that tell me whenever I'm using a synchronous coupling, i.e. the same one, or reflection coupling, i.e. one to be the reflection of the other. If you're in dimension one, this is just +1 and this is just -1. Yeah.
But it's important that you bring them in the compact set, you're not using a coupling, so you're using
Yeah,
something
I just let them be. Yeah, I just let them leave. Yeah, exactly. Exactly. So that's why I still need some confining to do. Okay, and just some technical assumptions so that it remains a Brownian motion. Okay, and so I have my coupling, and I can also construct my sort of semi-matrix. I take a modification of my standard Euclidean distance. It's something that you can usually do. You usually do when you're looking at second-order processes or kinetic cases. And you write a concave modification of your Euclidean distance, and you add the Lyapunov function. Okay, and so which basically means that when R is small enough, this will naturally decrease, and when R is big, this thing here will decrease. Okay. And at this stage, you take this quantity here, you use Ito's calculus, you derivate it in time, you see all the various behavior appearing in the calculation, you've got your negative terms that can only help you, and you finally use your Grandval lemma. Okay, I'm just keeping all those tedious calculations just to sort of go back to the result, which is to say that there exists a constant such that for interaction that is smaller than this constant, that is something that is necessary because you have counterexample of non-uniform time propagation of chaos in the sort of double wave potential, for instance. You've got uniform time propagation of chaos. I just gave them both the same initial condition for simplicity, but okay, we got this thing. Some references. So the coupling method I've just mentioned was created by Andreas Eberle to deal with the long time behavior of processes. And this method was adapted for uniform time propagation of chaos, and then in a kinetic setting, and then later on Katharina Schuh also created another type of method for such processes. Okay, my goal here was just to show you sort of the idea of a coupling method, which is to say there is a back and forth between the calculation and your intuition, in the sense that, okay, you expect your processes to come back to compact sets. So you use the Lyapunov function. You do the calculation and you realize that there is a naturally contracting subspace. So you're going to get particles closer to that subspace. Okay, so so you construct the distance and the coupling by hand. And then this type of ideas, you can also generalize it to other type of equations. So here's just an example of some work we've done with Laetitia Colombani. Here I have something that is a bit more exotic than the kinetic process I've just shown you. It's something that appears in neurosciences. Okay, each particle is actually a neuron, and each neuron is represented through two quantities: membrane potential X and the recovery variable C, which evolve according to this type of dynamics. And you can use a coupling method, the same one I've just shown you, to show propagation of chaos, uniform time propagation of chaos for dusting. Another type of example is if now you have your particles distributed according to a graph, and you want Here, your particles will interact according to a graph, meaning that psi ij is either 0 or 1, depending on if your particles interact with each other or not. So it's a bit more complicated because it's no longer exchangeable, but the same type of method can be applied. The one thing you assume is that your graph in the limits, so there's a force and then there's a interaction, your graph in the limit converges to sort of an homogeneous graph. And you can show uniform in time propagation of chaos to those sort of things using the same coupling method I've just shown you. Okay, and this is based on, this is work with Christophe Poquet, which was based on Delattre, Giacomini, and Musson. Okay. So if I want just to do like a very student-like pros and cons of my methods, I like the fact that it's quantitative because I explicitly build my distance, I derive it, and I have all my constant I can write. It yields and it uses sort of good probabilistic understanding of what's happening. Okay, you see the behavior of the particle translates in sort of the mathematical semi-metrics that you consider. It's quite robust in the sense that using the same ideas I can deal with different things. But no, notice that I've only spoken about sort of Lipschitz interaction, and one of my goals was to deal with singular interaction. The reason I can't do better than Lipschitz actually comes from this calculation here. Okay, at each time I need to do this sort of thing to use my law of large number, and now I need to deal with this difference here. I don't know how to do it. There were some cases, Samir Salem was able to do it in the case of bounded potentials, but okay. So far it's restricted overall to nice interactions. And the speed in n is not the correct one. This was shown by Lacker a few years ago. There is actually the optimal speed should be not square root of n, but n. I'll mention this later on, maybe if I have time. Okay, so this was the sort of probabilistic object, the sort of thing, the probabilistic method, the sort of things that I want to be able to do, but I just can't do it on singular interaction. So I'm going to use a PD method for a singular interaction. And the singular interaction I'm going to consider is the Biot-Savart kernel, okay, defined on R2 by this thing here. So you see that it explodes when x is close to 0. Sorry?
What is singular?
Singular, the fact that k of 0 equals plus to infinity, goes to infinity. Okay, so when two particles are close to each other, the interaction becomes singular. Okay, and as for the sort of physics behind it, if you take the 2D incompressible Navier-Stokes system, okay, and you take the curl of the equation, you find this equation here, okay, which is the nonlinear limit. So here, for instance, we're in a case where we have the nonlinear object, which comes from the physics, and I want, for instance, to be able to numerically simulate this thing. Okay, this is nonlinear. So what I can do is consider the particle system, which I can numerically simulate via some Euler-Maruyama scheme. And I want to be able to show that my, for instance, numerical scheme converges towards this. Okay, so it's an example where we see no longer this as an approximation of this, but that as an approximation of that. Okay. Okay, so this is the physics behind it. This is where the physics stop. I'm sorry.
Sorry, it would be like sort of a discretization.
Yeah.
Approximation in the sense of a discretization.
Of this equation here. Okay.
That equation would be a discretized version of the.
Exactly. Yeah, and this thing you can then discretize it again in time, this time, to put it in a computer. Mm-hmm. Some technical assumption is that I will work on the torus. This assumption was lifted a month ago and then this morning again. And I will consider my convergence in terms of relative entropy, rescale relative entropy because of the 1 over n. The results I'm going to focus on is the one that was by Jabin and Wang in 2018. And there are some assumptions that I'm going to specify later on, which are in particular satisfied by the Biot-Savart kernel on the torus. You can show non-uniform in time propagation of chaos. Notice that it resembles again the one thing that we have with the Wasserstein distance. Again, the propagation of the initial error, a correction term, and then something which comes from the Grandval. And the one thing we did was turn this into a uniform in time result. And the proof of this is what I'm going to focus on now. Quickly, why the one of the reasons why the relative entropy, it's not a distance, but it's quite a nice quantity because it controls usual distances. It controls via a Pinsker inequality the total variation distance or the usual L1 distance, and via Talleyrand inequality the Wasserstein 2 distance. Okay, so if you prove a convergence in entropy, relative entropy, you prove a convergence in real distances. Some references. So as I said, we're adapting the work of Pierre-Emmanuel Jabin and Zhenfu Wang. Before that, it was Fournier, Oren, and Michler who did something using compactness and tightness of measures. So non-quantitative result. The first quantitative one was here. On the torus, we made it uniform in time on the torus. Some parallel work by Rosenzweig and Sarfati, and then later on by Courcelle, Rosenzweig, Sarfati, using modulated energy, so another type of method. A few months ago, it was adapted on the entire space, and like this morning, so you can't really do much fresher than that. They made it uniform in time on the entire space. Okay, so if you're interested in this specific problem, you go see the last iteration of this work. I'm going to do sort of simplified version here. Okay. So, as I said, you consider your quantity, and now you're going to derive it in time. By direct calculation, you've got a quantity, a negative quantity that appears, which is known as the Fisher information, plus two terms that come from the fact that I have two different drifts. Those calculations, you do them by hand. And there's no assumption so far, okay. There's one assumption, is that I have the right to do the calculations. So I just assume that it's smooth. And because there is a logarithm here, I also assume it's bounded up from below and from above by a constant, which I can do because I'm on the torus. And I can just, if I want to be a bit more precise, I can just assume it's true for the initial condition, and then I can propagate this thing here. The second thing I'm going to notice is that this kernel K is divergence free in the weak sense, and it's bounded in L1. So in particular, this thing here disappears. Okay, so you're just left with this. Okay, and you notice that it once again resembles the sort of difference between my the K, the 1 over n sum of the K, and the K convoluted with rho bar. And the idea here is that K is singular, but rho bar is super smooth. So I'm going to use the regularity of rho bar to deal with the singularity of K. And it comes from the noticing that K can be written as the divergence of some bounded matrix field, which can be explicitly written in R2 because here I'm on the torus, I'm considering a periodized version of it. I need a small an abstract result on this. Okay, so now I can do an integration by part and go back to a bounded interaction. I do the calculations explicitly. Once again, I'm sorry, I'm skipping a lot of the calculations just now. Okay, and I get a part that was eaten by my Fisher information, and again, two things that resembles the terms that I had previously. Okay, now I integrate against rho Tn, so against the joint law of my particle system. If I wanted to use some form of law large number, I would like to integrate against independent things. I would like to integrate against my n copies of independent processes. The one thing that is nice with the entropy is that I can actually do a change of measure, reference measure. Integrating over mu, provided I pay an amount of which is the relative entropy of mu with respect to nu, and I also pay a logarithm of the exponential of my thing here, I can integrate now over nu. So what I'm going to do is pay the relative entropy of rho n, rho Tn with respect to rho bar tensorized n time, which is specifically the one thing I'm trying to control in the end. And I get independent processes. And with sort of large deviation estimates that come from Jabin and Wang, these exponential of this difference here, I can bound them by sum of 1 over n. Once again, skipping the calculation. And in the end, I get something like this. I get Jabin and Wang obtained something like this. They said this was negative, so I can just discard it. I use Grandval lemma, I get my non-uniform in time result. At this stage here, we want to get something uniformly in time. So I'm going to look at the constants and So I look more specifically at the constant. I'm going to try and show that it's uniform. It can be bounded uniformly in time. You see that the sort of derivatives of rho bar are appearing. And I want to use this negative term here to sort of get some diffusion of entropy. So I need two goals. I need what is known as the logarithmic Sobolev inequality, which is to say that this Fisher information will control the one term here, giving me this dispersion. And I need uniform in time bounds on the things that appear in my constant. For the logarithmic Sobolev inequality, I know that the uniform measure on the torus satisfies 1, which means that rho bar, which is bounded from above with respect to the uniform distribution, also satisfies 1. And one thing that is great with logarithmic Sobolev inequality is that they can be tensorized, meaning that rho bar tensorized n time also does with the same constant independent of n. So I get my Fisher information, which controls my entropy. And for the second part, I just do it by hand by induction. Okay, calculating. If you don't believe this result, the sort of thing that is hidden behind this is that if you look at this equation here, that you have some sigma here and that you have k, which is divergence free, it turns out the uniform distribution is the stationary distribution. And so if you start from any sort of initial condition, it's going to flatten to 0 or to 1, to the Lebesgue measure on the torus. And the fact that it flattens to 0 first was the one thing that told me that this thing was staying bounded with respect to the uniform distribution. It tells me, it's the one thing that tells me that my derivatives are bounded and that also they converge sufficiently fast to 0 that I can integrate it with time. It's the one thing, okay. It's the long-time behavior of the nonlinear process is actually what's hidden to find all those type of things that give me uniformity in time. And now with those two things, I can just sort of conclude. I get a minus term, a negative term that comes from the Fisher information. I have uniformity, and I can use my Grunwald lemma to conclude on uniform time propagation of chaos. Okay. So this was an example of PD method where we used the properties of the limit, namely its regularity, and also, as I said, in particular, its long-time behavior. And once again, we're not entirely sure. It might not be sharp in N. Okay, I mentioned a few times, and I'm going to go quickly on that, that the rate of convergence was wrong. Okay, for a while it was accepted, at least by me, that this rate here was optimal because it's the rate of the central limit theorem. But it turns out that using Babbage-Kawai hierarchies, Laqueur showed that this should actually be the real speed of convergence. And this can be done explicitly by looking at the linear case. So you know it's the sharpest thing. If you look at this thing here and you start from Gaussian measure, you know explicitly the solution of this take Gaussian, so you can compute everything. And you realize that you've got explicitly K over N. Okay, and so we know that we did not have the optimal rate of convergence. I'm going to skip. Okay, the fact that we obtained this square root of K over N by subadditivity, by looking at the general thing, and then by subadditivity we knew the speed of convergence for the marginals. He looked directly at Babbage-Kawai hierarchies, so more local approach, and it seemed more sharp. And so I'm going to end by saying that, okay, as I told you, the most exciting results concerning quantitative propagation of chaos for singular kernel use more like PD methods, so modulated energy, à la Sarfati, Babbage-Kawai hierarchies, even though there are remaining cases, few but remaining, kinetic cases, some technical assumptions, attractive interaction also is quite a complicated thing. And the question is, can we give probabilistic proof, i.e. coupling proofs of such results? And we would like, first of all, because I like probabilities, but also because it gets, it yields a better understanding, I believe, of the result of the processes. And can we obtain via a coupling method sharp rate of convergence? Okay, I'm going to end here and thank you for your attention.
Thank you, Pierre. So, is there any question?
So you didn't talk about very well these hierarchies that you mentioned.
Yeah.
So if I remember correctly, it's like giving equations satisfied by the K modules from the K+1 module.
Yeah, exactly.
So there are like hierarchies in differential equations.
Yes, of PDEs, yeah.
And are they related to like better known integrable hierarchies or other types of PD hierarchies, or we're just kind of coming with the other PD hierarchies, but they're a list of PDs.
So I'm not sure. I'm sorry, I'm not sure I quite understand. If do you mean like can you use previously known results on other things? That's not something I know quite well. I just the way I see it was just okay. You had exactly as you said a list of PDEs, and those PDEs were transport diffusion PDEs, which are obviously well studied. And along this hierarchy of PDEs, you just either write you obtain a hierarchy on the relative entropy, for instance, or la Jabin Wang solaire, Brecht solaire. Obtain, yeah, you have you assume that you have an LP bound on one of them, and you propagate that LP bounds on this second, etc. And from those propagated bounds, you can extract a convergent subsequence. Okay? Are they related to something that is already well known? That's I'm not sure. I would be saying something stupid.
What type of singular kernels in the cited example that you cited can be treated with these PD methods?
Okay, so okay. So in the case using modulated energy, suggested by Silvia Serpati and then extended with Rosenzweig, for instance, all those type of Friese interaction, provided they are repulsive. Okay, the attractive cases are still complicated. So then I would. Okay, so the Coulombian, the sub-Coulombian, and super Coulombian interaction can be done. Okay, S equals D is a threshold above which you can't really go because there for integrability reasons around the singularity. So yeah, I would be referring to those papers here. Okay.
There is a question from online audience.
Yeah.
Kami Ayati asks to see slide part 3 on singular again.
Yeah.
So
I'm there.
they can ask him to speak directly.
Yeah, so
I will cut my mic so that there is no.
So,
go back with my sound. So there are works by Bures, Jabin, and Wang on the Patlack-Keller-Segel, which is attractive cases, S equals 0 here, I believe, also log. There are some work by, to some extent, the Johan Tardy, Milica Tomaszewicz, on other types. It's a bit different, but it resembles those sort of things. Newtonian attractive, I'm not entirely sure. I don't think. Not. So, for instance, in the case of Patlack-Keller-Segel by Bures, Jabin, Wang, it comes from using the entropy plus the modulated energy to create something that they call modulated free energy. And it comes from the fact that the bad term that appears in the when you consider modulated energy is exactly the term that is controlled when you use the entropy.
Okay, so thank you very much again.
Thank you.
Your nice